Hey everyone, we are going to have a lesson on isotopes. This is lesson 2.4, and just a fair warning, isotopes are known to be very confusing, so I'm going to do my best to make sure that we're explaining this properly and that we all understand it. The warm-up question says, what is the average age of everyone in this class? You can go ahead and try to answer it. You don't have to do any calculation. But it should be around 15 and a half. Most people turn 16 during their sophomore year. Does that mean everyone is 15 and a half turning 16? No, there are some people who are older. There are some people who are already 16. There's also some people who are 14. But nationally, across the United States, sophomores tend to be 15 and a half. So pause the video. Think about why this is the case, and that's going to kind of help us go into this idea of isotopes. So when you're done, go ahead and restart the video. Okay, welcome back. This is a graph I put together. I have an Akita, that's my dog breed. You can go ahead and look it up on your phone or your laptop. You can see what they look like. They look like teddy bears. And the average weight of an Akita fully grown is about 110 pounds. We have a really big dog. But there are some cases where the Akitas can get up to about 170 pounds. They can also be pretty small and be about 70 pounds. But this is sort of an average. But if we had to say something like, well, what is the most common weight in pounds of an Akita dog? It would be where this bar graph is, right here, at 110. So this is kind of the most common weight in pounds of an Akita, and you can see here my graph is pretty labeled and everything. Now, this is really, really important because if you get an Akita, you are most likely going to have a dog that weighs 110 pounds. Now, does every single Akita weigh 110 pounds? No, but for the most part, they do. And all of these are measured in what our y-axis says is percent, okay? So every single one of these is a percent, and they're all going to add up to 100% of the Akitas that were reported that have a weight, okay? But it should be pretty obvious if I ask you what's the most likely weight of an Akita that you see on the street. It's probably going to be 110 pounds, okay? And this probably makes up, I don't know, judging by the graph, if this is about 1% down here, this is probably around, I don't know, 55%, and I'm just estimating. This would probably be 10%, 10%, I don't know, 30%. That might be over 100 already, but we get the idea. And this is about, I don't know, 12% or 15%. We get the idea. If you add all of them up, that should be a number close to 100. It should be actually exactly 100. Now, this is the same thing with elements. Not every element is going to have a specific weight or a specific mass in what we call it. But all elements have mass, okay? And that mass is measured not in grams, not in pounds, it's measured in AMU, which is atomic mass units. Okay, here I have almost the exact graph at what we just looked at, but instead we're looking at an element, and that element is silver. Okay. On the periodic table, it gives us a mass of silver, and that mass is 107 107.868. Okay? Now, with that being said, oh, and the atomic number of silver, so you guys can find it, is, I believe it is 47, but I could be wrong. With that being said, there are two isotopes of silver. There's silver with an atomic mass of 107, and there's silver with an atomic mass of 109. The atomic mass that you see on the periodic table is an average of these two isotopes. So if we were to multiply 107 times 51.84% and add that to our other isotope, which is 109, and multiply that by 48.15%, we would get a number very, very close to 107.868, which is what we see on the periodic table. Now, this goes for every single element, okay? Every single element has isotopes, and that contributes to its overall mass. Now, when we talk about isotopes, it's important that we know the definition of an isotope. And that was kind of like our precursor to what this all means. But an isotope is an element. So all elements are isotopes. But specifically, that element has the same atomic number, meaning it has the same number of protons but it has a different amount of neutrons. This means that the overall atomic mass will be different for the same element. Okay? When we talk about elements, it's super important, when we talk about isotopes, it's super important that we know this term abundance. And abundance is the relative proportions of each element that are found in nature. And when we say in nature, that just means like if we were to go outside and look, like what we would find if we looked for the element. And of course, these elements exist all over the universe. Now, even more specific, we can talk about the most abundant isotope. And this is actually pretty easy to figure out. But this is the most common isotope found in nature. Okay? Now, if we break this down, it all has to do with mass. So I want to start by saying the only two particles that contribute to an element's mass are protons and neutrons. Now let's think this out really quick. We know from our lecture last time that a proton has a mass of 1 AMU. And a neutron also has a mass of 1 AMU. So if the only things that contribute to mass are protons and neutrons, then every single atomic mass should be a whole number. Because you can't have less than 1 proton or less than 1 neutron. For instance, you can't have like half of a neutron or half of a proton. So the atomic mass should always be a whole number. But if we look at the periodic table, we can ask this question that's going to lead us into this term isotopes. Like, why do the atomic masses on the periodic table have decimals? And this can be answered because the atomic mass that you see on the periodic table is the average mass of all the isotopes of the element. And they do this using a mass spectrometer. They're able to decipher all of the different isotopes. They're very, very expensive machines. But let's look at an example. Let's look at a really common element, fluorine. And fluorine is atomic number 9, and it has an atomic mass of 18.998 AMU. Okay? Now there are 2 common isotopes of fluorine. The first one says that, well, fluorine will always have 9 protons, but the first isotope says that it has an atomic mass of 18. And this makes sense because if each proton and neutron weigh 1 AMU, then we should have nothing but a whole number here. The other isotope of fluorine says that it has an atomic mass of 19 AMU. So why does the periodic table tell us that fluorine has a mass of 18.998? Why does the periodic table tell us this? And it's very, very simple. This is an average of the isotopes. But it's not just an average of 18 and 19. It's an average of the isotopes and how abundant they are in nature. So let's take a look at 18.998. This is the average of the isotopes and how abundant they are in nature. This number is so close to 19, and it's still about 1 AMU away from 18. So if we were to estimate how frequent we would see each of these in nature, I would say we see about 99% of fluorine 19? And I would say we would see about 1% fluorine 18. And you can do this with almost every single element on the periodic table because every single element has isotopes. But what we want to do as part of this class is we want to be able to recognize how many protons, neutrons, and electrons an isotope has. And we want to be able to determine if it's the most abundant. Okay? And we can do that pretty easily. But let's take a look at my favorite element, which is ruthenium. Ruthenium on the periodic table looks like this. 44 Ru. It's got a nice little element name, and it has a mass of 101.07. So this is what it looks like on the periodic table. Now what you'll have to do is you'll have to decipher between ruthenium's 4 isotopes. So ruthenium 99, ruthenium 100, ruthenium 101, and ruthenium 102. So these are the isotopes of ruthenium. And we want to know if we can break down how many protons, neutrons, and electrons are in each of these isotopes. Now I'll tell you, the protons and the electrons are going to be very, very easy to decipher. Why? Because every single ruthenium atom has an atomic number of 44, which means that every single one of these protons will be 44. Now, there's no charge on ruthenium right now. It's not like we're talking about Ru plus or Ru2 plus. So we're going to assume that the number of electrons are the same as the number of protons unless we're told otherwise, or unless we see a charge. Now, the number of neutrons are going to be a little bit more complicated to find. In these isotopes, we're given a value, and that value is the atomic mass of the isotope. And it should always be a whole number, and you can see we're only given whole numbers here. And if we think back to our notes, or if we remember from our notes from last time, the atomic mass is the number of protons plus the number of neutrons. So to find the number of neutrons, we have to take the atomic mass we're given, subtract it by the number of protons, and we should get the number of neutrons. And we can do that for each of these. And ruthenium-102 would have 58. Notice how my number of protons didn't change. We didn't change the element, so we didn't change the number of protons. Okay? If we were to change the number of protons, then we'd have a different element. Now the question is, what is the most abundant ruthenium isotope? And the way that we do this is we look at what the periodic table gives us. And the periodic table says the average atomic mass is 101.07. So we're going to make an assumption, and we're going to say that ruthenium 101 is the most abundant isotope. Because it's closest to the number on the periodic table. And that isotope has 44 protons and 57 neutrons. If we were to go find ruthenium in nature, or if we were given a block of ruthenium, I don't know, by some scientist, it's most likely that it will have 57 neutrons, and it will definitely have 44 protons. So this is definite, and this is highly likely. A couple more things that you're going to have to do is you will have to write the most abundant isotope. And it's actually pretty simple to do this. You'll be given an element. So let's work with a couple, so we can do a couple examples. If we're looking at the element vanadium, it's abbreviated V. It has an atomic number of 23, which means it has 23 protons. And it has an atomic mass of 50.942 AMU. So if we're writing the most abundant isotope, we write the name, we put a dash, and then we write the closest atomic mass in a whole number to what's seen on the periodic table. So in this case, it's going to be vanadium 51. And this is how we write the most abundant isotope. You could also write it like this, with the element symbol and the atomic mass on top. So either of these are acceptable. Let's do one more. Let's do neon, which is Ne. Neon has an atomic number of 10, which means it has 10 protons. And the atomic mass is 20.180 AMU. So if we are going to write the most abundant form of neon, 20.1, we're going to round down, so it's going to be neon 20. We could also write the element symbol Ne and put 20 on top. So either of these are acceptable. Both are correct. The last thing that you want to do is be able to recognize if something given to you is the most abundant isotope. So let's take a look at something I'm going to give you, which is calcium 45. And we want to know the number of protons in calcium, the number of neutrons in this specific calcium we're given, the number of electrons, and we want to know, is it the most abundant? So calcium on the periodic table, and I'm going to draw this out, you don't have to, but it's 20, it's got a big Ca, and because I don't have space, I'm not going to write the name. Actually, I will, calcium. And on the bottom, it has 40.078. So again, the number of protons do not change ever. We're talking about calcium, so it has to have 20 protons. Doesn't seem to be charged, so it has 20 electrons. But the number of neutrons is going to look a little bit different in this case. We're given an atomic mass of 45. So we have to use this atomic mass to now calculate the number of neutrons in this specific isotope, which is 35. But we know that the most abundant isotope is on the periodic table. And that has an atomic mass of which we will round to 40. So the most abundant isotope has 20 neutrons, not 20, I'm sorry, this should be 25. We know that the most abundant isotope has 20 neutrons, not 25 neutrons. So when we're asked if it's the most abundant, we're going to say no. If this number was 20 and this mass was 40, then we'd have the most abundant isotope. Anyways, there is a worksheet for you to do. Let me know if you guys have any questions, and